Hello students, welcome in video lecture of subject heat transfer. Topic of this lecture is Introduction to Heat Transfer. After watching this lecture, you should be able to explain heat and heat transfer, define steady and unsteady heat transfer, describe modes of heat transfer, conduction, convection and radiation, explain laws of heat transfer, describe Fourier heat conduction equation, describe the terms thermal conductivity and thermal diffusivity, and determine the heat transfer rate. Now let's start. The subject heat transfer is a branch of thermal science which deals with the analysis of rate of heat transfer and temperature distribution taking place in a system as well as the nature of heat transfer. Now, what is heat transfer? Heat is a form of energy, is transit due to temperature difference. Heat transfer is transmission of energy from one region to another region as a result of temperature difference between them. Whenever there exists a temperature difference in a medium or within medium, heat transfer must occur. The amount of heat transfer per unit area is called heat transfer rate and it is denoted by capital Q. It has a unit joule per second which is equivalent to watt. The rate of heat transfer per unit area normal to the direction of heat flow is called heat flux. Heat flux Q equal to heat transfer rate Q divided by A, where A it is the area perpendicular to direction of heat flow. The unit is watt per meter square, and where A area perpendicular to the direction of heat flow. Now, steady and unsteady heat transfer. For analysis of heat transfer problems, two types of heat transfer are considered: steady state and unsteady state. In case of steady state heat transfer, the temperature at any location on the system does not vary with time. The temperature is the function of space coordinates only, but it is independent on time during the steady state condition. In unsteady state heat transfer, the temperature vary with time as well as the position. The temperature is function of time and space coordinates. Steady state heat transfer, T is the function of X, Y, Z, means only coordinates. In unsteady state heat transfer, T is the function of X, Y, Z, means coordinates, and time T. Now, modes of heat transfer. Heat transfer, which is defined as the transformation of energy from one region to another as a result of temperature difference, takes place by the three modes: first conduction, second convection, and third radiation. Heat always flow in the direction of lower temperature or from higher temperature to lower temperature. This is the direction of heat flow. Now, conduction. Conduction is the transfer of heat from one part to or from one part of substance to another part of same substance or from one substance to another in physical contact with it without an appreciable displacement of molecules forming the substance. In solid, the heat is conducted by two mechanisms. First, by lattice vibration, this is major part. Second, by transport of free electrons. Now, convection. Convection is the transfer of heat within a fluid by mixing of one portion of fluid with another. There are two types of convection: free convection and forced convection. The next, radiation. Radiation is the transfer of heat through space or matter by means other than conduction and convection, or it is by electromagnetic waves. Now, heat transfer by conduction. The Fourier's law of heat conduction, it is empirical law based on observation. Fourier law states that the rate of heat conduction per unit area, which is heat flux, is directly proportional to temperature gradient. Heat flux Q means Q upon area. This is heat flux is proportional to dt by dx. This is temperature gradient. This is the solid of thickness dx and this is area A. Then heat transfer Q, which is perpendicular to area. So Q by A, this is heat flux. Then Q by A, heat flux is proportional to dt by dx and equal to minus K dt by dx. Because dt by dx always negative, then negative and negative positive are Q equal to minus K A dt by dx. So heat transfer rate Q equal to minus K A dt by dx, where K equal to constant of proportionality and is known as thermal conductivity. The unit of K, unit of thermal conductivity, this is watt per meter Kelvin or watt per meter degree centigrade. For a slab, one side temperature T1, other side temperature T2. The thickness of this slab is L and conductivity K constant. Then by Fourier conduction equation, heat transfer Q equal to minus K A dt by dx or Q into dx equal to minus K A dt by integrating Q integration dx minus K constant, area constant, and on one side temperature T1, on other side at length L, thickness L, temperature T2. Then Q into L equal to minus K A T2 minus T1 or Q equal to Ka T1 minus T2 divided by L. So this is the heat transfer through a slab having constant K and cross-sectional area A. The following assumptions on which Fourier's law is based. First, conduction of heat takes place under steady state condition. Second, the heat flow is unidirectional or one directional heat flow. Third, temperature gradient is constant and temperature profile is linear. There is no internal heat generation. Fifth, boundary surfaces are isothermal. And sixth, the material is homogeneous and isotropic. Now, thermal conductivity. Thermal conductivity is the property of material and is defined as the ability of material to conduct the heat through it. Thermal conductivity of material is a measure how fast heat will flow in material. The large value of heat conductivity indicates that the material is good in heat conductor, and low value indicates that the material is a poor heat conductor or insulator. Thermal conductivity of material varies with temperature. The unit of thermal conductivity is watt per meter Kelvin or watt per meter degree centigrade. Heat transfer by convection. Now, Newton's law of cooling, it is a fundamental law of convection, and it states that the rate of heat transfer is directly proportional to temperature difference between fluid and surface. Q means Q by A is proportional to temperature difference. Surface temperature minus temperature of fluid. This is the surface having temperature Ts, and this is fluid of mean temperature Tf. So heat transfer from surface to fluid when Ts greater than Tf, then Q equal to, or heat flux Q by A equal to is proportional to Ts minus Tf, or Q is proportional to area into temperature difference, or Q equal to H constant multiplied by A into Ts minus Tf, where H is heat transfer coefficient. So heat transfer by convection, Q equal to HA Ts minus Tf, and it can be written as Q equal to Ts minus Tf upon 1 upon HA watt or joule per second, and unit of heat transfer coefficient is watt per meter square Kelvin. This is the unit of H. Next, the heat transfer by radiation. Now, the Stephen Boltzmann law of thermal radiation, it states that the rate of radiation heat transfer per unit area from black surface is directly proportional to 4th power of absolute temperature of surface, is proportional to T power 4, when this is the surface of absolute temperature T, then heat transfer from this black surface Q is R. Q is proportional to area into R. Q equal to constant, which is called Stephen-Boltzmann constant, into A into the unit of sigma watt per meter square Kelvin power 4. So heat transfer by radiation sigma A Now, isotropic and anisotropic material. If the thermal conductivity of material does not vary with change direction or its value is in same in all direction, then material is called the isotropic material. If the thermal conductivity of material depends on the direction of heat flow, the material is called anisotropic material. For example, wood. Now, thermal diffusivity. Thermal diffusivity is an important thermophysical property. It is the ratio of thermal conductivity K of medium to heat capacity rho C. It is denoted by alpha. It is the ratio of heat conducted through material to heat stored per unit volume. The unit of thermal diffusivity is meter square per second. It is the ratio of thermal conductivity K divided by density into specific heat capacity. So alpha equal to K by rho C. The unit of alpha is meter square per second. Now let's solve some problems. Problem 1. A composite wall consists of two layers of different materials having conductivity K1 and K2 for equal thickness of two layers. Determine the equivalent thermal conductivity of the slab. Now we solve it. T and A be the thickness and area of wall. First we draw the schematic diagram. This is wall 1, wall 2, given equal thickness means T and conductivity K1 and this is K2. Let T1 the surface temperature T1, on other side T2, or this is Ti. Now heat transfer from T1 to Ti, this is Q1, and from Ti are at this temperature to T2, this is Q2, where Q1 equal to Q2 and equivalent slab of thickness T plus T 2T and temperature T1, here temperature T2 and equal thermal conductivity K equivalent. Now heat transfer rate Q1 equal to temperature difference T1 minus Ti upon T upon K1A, and Q2 Ti minus T2 upon T upon K2A, where Q1 equal to Q2, Q1 equal to Q2, which is equal to T1 minus Ti upon T upon K1A equal to Ti minus T2 upon T by K2A. And it can be written T1 minus T2 upon T upon K1A plus T upon K2A. Ti cancel out, and from this equivalent slab Q equal to T1 minus T2 divided by 2T upon K equivalent A. From equation 1 and 2, T1 minus T2 upon T by K1A plus T by K2A equal to T1 minus T2 upon 2T upon K equivalent into A. By solving above equation, we will get K equivalent equal to 2 K1 into K2 divided by K1 plus K2. So this is the answer. Problem 2. A 0.5 meter thick large plane wall has its two surfaces capped at 300 degrees centigrade and 200 degrees centigrade. The thermal conductivity of wall varies linearly with temperature, and its value at 300 degrees centigrade and 200 degrees centigrade are 25 watt per meter Kelvin and 15 watt per meter Kelvin respectively. Determine steady heat flux through it. Now we solve it. Conductivity of wall K equal to A plus BT, means K is the function of temperature which is linearly. Now at 200 degrees centigrade, the thermal conductivity is 15 watt per meter Kelvin, and at 300 degrees centigrade the thermal conductivity is 25 watt per meter Kelvin, which is increased linearly. And at temperature T, the thermal conductivity is K. Now draw a line perpendicular to AB, and this is CE, this is BD. So BD upon CE divided by AD upon R, 25 minus 15 upon K minus 15 equal to 300 minus 200 divided by T minus 200. Then K equal to conductivity K, it is T by 10 minus 5, means K, it is T by 10 minus 5. Now applying, so this is the slab of thickness 0.5, K, which is vary with T, temperature 300 degrees centigrade, and on other side 200 degrees centigrade. Now applying Fourier's heat conduction equation. So heat flux Q equal to minus K dt by dx, or Q into dx equal to minus K into dt, integrating Q, substituting K, T by 10 minus 5 into dt, and integration from 0 to 0.5 and 300 degree centigrade to 200 degree centigrade, or Q into 0.5 equal to 5t minus t square by 20, 300 to 200. By solving, we get Q equal to 4000 watt per meter square. This is the answer. For more practice, please solve the questions given in assignment sheet. Questions are based on Fourier's conduction equation and also asked in previous year's GATE exam. Now note down the questions. Any query or doubt, please write in comments box.